Hello everyone, welcome to my CCI Enterprise course. In this course, you will learn all the technology related to your CCI Enterprise journey. And in case if you are looking for the actual lab type of scenario and the solution, then you can reach out. You can send me email ratnesh721kumar721 that is here, and then I will send you that detailed info that how my students they are preparing for their actual lab training. It will be almost similar that what you will expect in the exam. You can practice. I will help you. I will guide you for 1 month to clear this exam. I will help you step by step how to drill down um, the solution, drill down the technology into small pieces, and I will help you to pass your exam in first attempt. So go for this course. This will be a good place where you can learn the technology. But if you are serious about the CCI lab exam, then you can drop me an email and you can get the detailed info. All right, so let me stop this video, and if you watch this video, you can simply contact me and you can get the information related to the new update that we have in the CCI Enterprise Lab. In section 1.10, we have to understand about OSPF and OSPF related troubleshooting tickets. What I have done, first of all, I have covered the theory related to OSPF plus the lab. So the idea here is this, that you please complete the OSPF related theories and OSPF related labs, not only OSPF version 2, but OSPF version 3 as well. So you will find videos related to OSPF version 2, and let me mark. So 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 videos related to OSPF version 2. And then I have added OSPF version 3, that is IPv6 version of OSPF. So 2 videos related to that. Please complete these videos. Once you complete, then the OSPF troubleshooting videos will start. So please complete up to here, and then you will find troubleshooting related videos. Let's start with OSPF. Now, OSPF, that is Open Shortest Path First Protocol, is a link state protocol like ISIS. Now, what link state protocol is doing, that instead of sending the entire topology table hop by hop, they are sending the state of a link to the neighbor device. Now, how this technology is working, and let me try to draw here. So generally, all the link state protocol, they are forming, first of all, the neighbor table. So they are sending the update to all the adjacent device or the neighbor. With help of neighbor table, they are forming the topology table. Sometimes we are referring this as a entire database as well. And finally, they ran the SPF algorithm here. From the topology table, they are going to form the best path, that is the routing table. So we have three different types of table: neighbor table or database table, topology table, and then finally the routing table. Now the mechanism behind this and the theory behind this we'll see in upcoming slides. So OSPF is entirely dependent upon areas. Generally, we are telling that we have one backbone area. So here you can see that you have area 0, and logically all the areas are connected with area 0. Now these areas are 32-bit. They can be a flat number, or you can define like in dotted representation 000 like this. Areas has continuous means area. You can see that you have area 0 and then area 1, 2, 3. Um, so maybe you can think that can't I connect area 3 with area 5 or 4? Yes, we can do that connection, but you can see that area 4 is not directly connected with area 0. So somehow I have to create tunnel, or the area 3. Uh, I have to create area 3 as a tunnel, or we have to use some sort of virtual link. So area 4 can think that he is directly connected with area 0. So such type of arrangement we need to do, and then the link state advertisement will flow from one place to other place. That's the LSA, correct? Now, OSPF send LSA when there is a change to one of its link and will only send the changes in the update. LSAs are additionally refreshed by after every 30 minutes. So how we can summarize it, that OSPF is a link state protocol dependent upon area. They are sending their LSAs or their advertisement to all their neighbors, and with that they are forming the neighbor table, topology table, and finally the routing table. Apart from that, that OSPF traffic is multicast. They are using 224005 for all the routers and 224006 for the designated router. The theory behind this we can discuss in upcoming session. They are using the Dijkstra shortest path first algorithm to build the routing table from the topology table, and they are supporting the variable length subnet mask. So here you can see that first of all they form the neighbor table, then they form the database, then they do their algorithm, that's the SPF algorithm, Dijkstra's SPF algorithm. Finally, they will form the best part table, that is the routing table. OSPF supports IP routing. Their AD value is 110. Their cost, their metric is cost. They are going to form the neighbor table, topology table, and routing table. Uh, all the areas should be supposed to be connected with a backbone. That's the area 0. If we have non-backbone area connected with any other area, then you have to create tunnel or virtual link in between that. Now, suppose we have such type of topology here. You can see that I have area 0 connected with area 1 and area 2. So now what we are going to tell about these devices, these routers, router A and C, they are termed as a ABR, area border router. They are termed as a ABR, area border router, because they are in the border of different areas. Okay, and we'll see that according to that the routes are also going to get reflected. So when we are talking about the routes, you'll find that you have O routes and then OIA, that is OSPF intra area. So you have two type of route, OSPF intra area route, that is this. Then you have inter area, across the area, that is this, and we'll see that we have E1 and E2 routes as well, that is coming from the external as well. Now if you see this diagram, it's actually very simple, straightforward, that we have 2 or 3 routers in area, but assume that if you have 50 or 100 routers in area, and suppose if I have 200 routers and all the 200 routers are inside area 0. So at that time, what will happen? The computation, means to run that SPF algorithm, becomes CPU intensive, rather than if you have a small areas and then you have 50 device, 100 device, and 50 device in those areas. So in that case, all the areas they will run their independent SPF algorithm, and then they will send the update to the backbone. So in that case, the way that we are going to run the SPF algorithm, or in other words, the process, the CPU utilization, the memory will be optimized and will be used betterly, because now you're running the SPF algorithm across small areas, and then those areas are going to send their LSAs to the core or to the other areas, correct? So that's the thing, and that when we are that's why we don't have only area 0, rather than we have multiple logical areas, and then we are going to divide the devices or the routers inside the area. Then here you can see that suppose in case that if you have device and that is not connected with the area 0. So in that case, you have to create the virtual link, the device which is separating the area. They are termed as a ABR. Then you have internal router, then you have backbone router. Again, these are just the terminologies. All right, now here you can see that you may have chance that you are connected with non-OSPF protocol. So you are getting the route, say for example, from the EIGRP domain. So in that case, that router is termed as a ASBR, Autonomous System Border Router. So now here you can see that C and D, they are ABR, Area Border Router, but router G is ASBR because now the routes is coming from the other routing domain to the OSPF. Okay, so uh, here you can see that if we have any other routing domain that will term as a separate autonomous system, and then you have to do the redistribution. Obviously the router G will do the redistribution from EIGRP to OSPF when it is coming to OSPF, and OSPF to EIGRP when you are sending your update to the EIGRP domain. Now in that case, we have E1 and E2 type of area. Now what is E1 and E2? Here you can see by default it will be OSPF external area type 2, that is the E2. So include only the external cost to the destination network. External cost is the metric is cost advertised from outside the OSPF domain. This is the default type. Then you have E1 that will also have the metric value, that is the cost, but this will be additive, means it will add the cost per hop per router. So include both the external cost and the internal cost. So that's why you have the external cost plus the internal cost to reach uh, the ASBR to determine the total metric. But E2 having only the external cost, that will be constant. So in summary, here you can see that you have internal routers, that all router interfaces belong to only one area. You have ABR, you have ASBR, you have backbone router that is inside area 0. Okay, so this is the baseline summary for the OSPF routing protocol. In the upcoming sessions, we will learn more about OSPF terminologies, and we have to perform the lab as well. So what type of LSAs we have in OSPF? OSPF has a long list of LSAs. We are going to discuss the top 5 at least because these we are going to use more and more in the course. So we have LSA, here you can see type 1 and type 2. Now these type 1 and type 2 LSAs are reside within the area. They are very much area specific LSA. Then we have type 3 and type 4 generated by ABR, Area Border Router. They can flow from one area to other area. We'll see in the upcoming slide. And then we have type 5 LSA that is generated by Autonomous System Border Router, means non-OSPF protocol. They are going to generate that. Now here you can see the detailed explanation of all the LSA. Type 1 is LSA and type 2 as well. They are within the area. Use of type 1 LSA is that they have the link, obviously the status and the cost of all those links, and they are generated by all the routers in a network. So you can think that type 1 as a default LSA generated by all the routers within that area. Then we have type 2 LSA generated by DR in the OSPF network or OSPF domain. Again, this is also specific to the area. When we have the broadcast type of network, obviously that time the DRBDR will come into the picture. Then we have the network summary LSA, that is type 3. What it is doing, that generated by ABR, and this can be used for inter-area communication. We'll see that all the places you have this inter-area link. So you have area 0 connected by different areas, and all these ABR shown in the diagram, they are going to generate type 3 LSA to do this inter area communication. Then we have ASBR summary. Now the next question here is, suppose from OSPF inter area, you have to reach to non-OSPF domain. So for that reason, we have autonomous system border router summary LSA, means somehow you need to reach, or somehow you have a route to reach to the non-OSPF protocol. Then we have external LSA type 5. Now this is generated by the ASBR, and this information will be flooded inside all the areas. So all the areas, if obviously you have the redistribution, all the areas should know how to reach to the autonomous system border router or the network behind the ASBR. We have type 6 as well, that is the multicast OSPF, type 7 as well, that is not so stubby area. And this type 7 is actually very important, and we'll discuss this later on. Now here in the diagram you can see that you have area 1, area 0, area 2. So belonging to area 1, area 2 and area 0, you have this router and network LSA, means type 1 and type 2 LSA will be generated in that. Then you can see that router C and D, they are ABR, so they are going to generate the type 3 and type 4, and then router G is belonging to ASBR, he is going to generate type 5 LSA. Okay, great. Then how this OSPF is going to form the OSPF neighbor relationship. So if you go and connect two OSPF or two routers in between, so suppose for sake of simplicity, I have only two routers connected in a network. So in that case, what will happen? Suppose I have router 1 and router 2, and these two routers are connected, or they are inside area 0. So obviously these routers, because they are within the area, and suppose if it is a point-to-point network, then they will send and receive the router LSA, correct? So what will happen, that they are going to send their hello packet in the point-to-point network, or in the broadcast network. This hello timer is 10 seconds and dead timer is uh, 40 seconds, so it's 1 into 4. And in the broadcast network, actually in the NBMA network, that will be 30 second, and then the dead timer will be 30 into 4, that is 120 second. So they will send and receive, they will exchange their hello packets, and if they are matching certain criteria while sending and receiving the hello packets, then they are going to form the neighbor relationship. So here you can see that what are the things inside the hello packet, or what are the fields inside the hello packet. They contains area ID, area type, prefix, subnet mask, hello interval, dead interval, network type, and authentication. Basically it is termed as that they have 8 field inside hello packet, and you should match at least the area ID, the subnet mask, hello and dead interval, authentication, etc. So some fields are mandatory that should match in between two routers to form the neighbor relationship. Okay, so here you can see that a neighbor table is constructed from OSPF hello packet, which includes the following: the router ID, the current state, directly connected interfaces, and the IP address of the remote interface of each neighbor. We'll see that in the lab section, and we'll go and we'll run the command show IP OSPF neighbor, and then we can see the specific about the neighbors. Now the next topic here is that OSPF designated router and backup designated router. So what is happening and how they are going to form the DR BDR, or how they are doing the selection for the DR BDR. Let's discuss about that. So here you can see in the diagram, first of all, these devices, they should have their priorities. So let me show you what I try to tell here. I should have slide for that. Yeah. So here you can see that that these devices, they have their unique identification. That's the router ID. All the routers in a network, they have the router ID. We can configure it manually, or suppose if device has the loopback interface, or they have the physical interfaces, first of all they will check the loopback interface if you are not doing it manually. So that loopback interface will become the router ID, or the highest physical interface will become the router ID. So they should have the router ID. That will be by default if you're not doing it manually. Once they have router ID, then they are going to do the DR/BDR selection, and this selection will happen only in the broadcast network. So here you can see in the diagram that if we have router ABCD connected with a shared network or the broadcast network, so at that time they will go and select the DR and BDR. Okay. Now, what will be the selection criteria here? The DR/BDR selection are determined by the router's priority, which is configured per interface basis. The router with the highest priority becomes the DR, and the second highest will become the BDR, and the rest are DR brother, something like DR, BDR, others. Okay. Now, if there is a tie in the priority, whichever router has highest router ID, that will become the DR. Now we can go and set this priority like this also, like we can go to the interface and we can set IP OSPF priority, and then we can force to make certain device as a DR or BDR. Now by default the priority will be 1, so obviously the selection will happen with respect to router ID. So whoever having the highest router ID in the network, that will become DR, BDR, etc. like that, in that manner. Suppose if you don't want that certain routers or device will take part inside the DR, BDR selection, so you can go to the interface and you can set the priority as a 0. So if you set the priority as a 0, that device will not take part inside the DR, BDR. Okay. So what are the important things we have studied in this video? That type of LSA, then how they are going to form the OSPF neighbor relationship, what are the important fields you have inside the hello packet, all the devices they are sending the hello packets to the peer devices or the neighbor devices to form the neighbor relationship, then how they are going to form the DR/BDR selection. Again, the router ID will be important factor here, and as per the router ID they are going to form the DR/BDR, because by default we are not setting the priority. By default the priority will be 1, and according to the router ID they will select who is the DR, who is the BDR. Let us learn more about OSPF neighbor state, and then I'm going to perform one small lab task where we'll understand more about the OSPF process, OSPF actually neighbor process, and even the baseline commands of OSPF as well. So now when the OSPF, the first stage is that they have to form the neighbor relationship. When they are forming the neighbor relationship, at that time they are exchanging, or they are going through a process, or they are going through multiple steps. So what are those states we have? Here you can see that they will start with a down, init, two-way, etc. So in down state indicates that no hellos has been exchanged, but the actual process will start from the init state. Init state, the devices they will start sending their hello packets. We know that inside hello packet we have some important fields. Few of them are mandatory, like the area, like the authentication, uh, the network subnet, etc. So few of the fields are mandatory, that two sides or the neighbors, they should match those mandatory things. Then they will go to the two-way state. By the end of two-way state, uh, the devices, if they are in the broadcast network, they have to select the DR and the BDR. And by the end of two-way state, the devices, they are forming the neighbor relationship. Okay. Then we have the external start and external exchange. Now external start and exchange is a state where the devices, they have to select that who is the master and who is the slave, so they can exchange their databases. So obviously the devices, they are sending their link state or LS information to each other to build the database. Once they have the database as per the uh, master and slave entry, as per the master and slave rule, they have to exchange their LS type. Correct? So someone may sending say link state advertisement, someone may asking link state request, so LSA, LSR, those things are going in depth when we are talking about the exchange state. Then we have loading, where all the devices they have to sync their database, and by the end of this loading state, the OSPF process, they are forming the topology table. Remember, we have three important table. We have neighbor table, so by the end of two-way state they will form the neighbor table. We have topology table, by the end of loading the devices will form the topology table. And finally, once they have the topology table, on top of that the devices will run the SPF algorithm, shortest path first algorithm, and then they have to form the routing table. We'll see that if we have the broadcast network, then they will have the rules like DR, BDR, and DR other. All right, so here you can see that suppose in broadcast network, if we have these rules, this DR other, they will go and stop at the level of two-way, because what is happening in that situation, in that case, is that you are giving the authority to DR and BDR to exchange all the LSAs with all the other, rather than all the other DR others, they are exchanging their database packets. So that means they will stuck at the two-way state, means all the DR others, they will stuck at the two-way state, they will not have the full authority to exchange the databases. Correct? All right, so we have a small lab topology. In this first lab, just to start with, what we are going to do, that we will go and initiate the OSPF process. So let me show you this. Although we have this master lab topology, what we can do as per our requirement, will go and use it. So what does it mean? That we'll go and make these devices, say for example R1, R2, and switch 101 within area 0 at the moment. So they will be the part of area 0. And this switch that you are seeing here, switch 105, that I will make as a switch only. Later on we will make this as a L3, but at this point of time, I assume that I have R1, R2, and switch 101, and the IP that I am going to use, the IP will be, say, let me write here the IPs, and according to that I am going to configure the lab. So the IPs that I want to use is, say for example 10.1.1.1 and 10.1.1.2 as per the name of the devices, and here, so for example 10.1.1.101, they are inside the same broadcast network. So you can see that they will go and form the DR and BDR. Loopback addresses I will give like 111, and then this I can give 2222 as the name of the device, and this I will give as 101, 101, 101, 101. Okay, we are going to initiate the OSPF process inside area 0, and then we'll see that how they're going to exchange all those hello packets and the important LS type. All right, so let me go and log into the lab devices. All right, I logged in, and we know that we have other interfaces and links also connected that I don't want. So this is the topology that we have. What I can do here, that I will start with 101 E1/2. So let's do that. I can go to, first of all, let's see this neighbor. and I want to shut down few of the interfaces that I don't want to use. So for example, I want to use only interface 1/2, so 0001 and 1/2. So 0001, so I can do one thing, interface range E0/2 to 3, shut down, interface E1/0, shut down, because I want to use 1/2 only. So rest of the interfaces I'm making shut down. Like that, 1/1 also I want to make shut down. If I go and check show CDP neighbor, so I have 0001 and 12 that I want to use. Now next I will go to switch number 2. So switch 2 is not required in this particular lab, so leave it. Then I'll go to switch number 5, and we should check this E1/2 configuration as well. So I will go here and check E1/2, and what is configured here? Nothing is configured. If nothing is configured at this point of time, at least what we can do is we can make this interface as a switch port. Correct. So here you can see this capabilities R, S, and I, and that I don't want. I'll make this as a switch port. Then we'll go back to the switch number 5. Here you can see, and the interfaces we have is 0, 0, 1, 2, 3, and 10/0. So apart from that, what I want, that I want to make other interfaces as a shutdown, and we have so many interfaces. Here you can see, even we can leave it as well, just to check the configuration for any of the interfaces. Say so run interface E0/0 that is connected with router number 1, and then router 2. So these are the interfaces connected. I don't want to do anything, rather I will do one thing, that interface range E0/0 up to, for example, 4 maybe, and 3. I'll make this as a switch port and no shutdown. And then interface E10/0 that is connected with switch number 1, that if you see here, switch number 1, what interface we have here, let me scroll up, 10/0, yeah. So I can go here, interface E10/0. I'll make this also as a switch port, no shutdown. Alright, so we are very much good with switch number 1 and switch number 2. Here again I can go to interface E1/2. I'll make this as a switch port, no shut. Alright, so let me quickly see here that what I exactly required. So E1/2 should not be switch port. It should be a routed port. So I'll do no switch port, and then I'll assign the IP address. So for example, 10.1.1.101, and then I'll create one loopback, say loopback 0, IP address 101 and 101.101. So what I have done here, we can check show IP interface brief. So I have interface E1/2 and one of the loopback interface where I have assigned the IP addresses. Okay. All right. Great. So now we can go to R1 and R2, and the interfaces you can see here. So I'll go to R1 first, and I can go to interface E0/0. I'll assign IP 10.1.1.1, and then I can do ping just to check that the switch far end switch is reachable or not. So it is reachable, then I'll go and create one loopback, say 0, and IP address I'll give 111 to that loopback. We'll go and check the show IP interface brief, so you can see that we have the IP configured here. Now let's go to R2, and inside R2 we have interface E0/0. I can go and give the IP like this, and then I'll create one loopback 0 where I can give IP related to as per the diagram or as per our schema 22222, and then let me try to ping. First of all, within the same network, obviously everything is inside the same network for this example. So what I'm doing, that I'm pinging to all the devices from R2. So now we have the baseline IP address connectivity connected. The thing here is that we are going to enable the OSPF to all these devices, and we are assuming that all these devices are inside area 0, correct? So let's do this, and let me go back to the lab. Yeah. So before doing that, at least one of the device I want to enable the debug. So I want to enable the debug OSPF packets and events, debug IP OSPF packets, and then I want to enable the events as well. Okay, let's do this OSPF configuration. So we can go to router OSPF, and then you have to define the process ID, say 1 I'm giving at this point of time. Then I should go and advertise the network. So network is, I have two network, one is 10.1.1.0. I can go and give the wildcard bit inside area 0. So this is the format that we can go and enable the OSPF. And at the moment I enable that, you can see that we have event because we have enabled the debug as well. You can see that this router using this multicast address, and the router ID is get selected as 11111. We have discussed this earlier. If I go and check show IP OSPF, you can see the red router ID is 11111, and we have the other information as well. Okay, so we have the OSPF configuration, and periodically he is sending the hello packet. We can go and check the configuration for that, what we have done. So we have enabled the OSPF process, and then we have advertised the network, correct? So likewise, I can go here and initiate the OSPF process here as well. Then I can go and I can assign the router ID via the CLI command as well, means manually as well. But if you do not do this, automatically they will take this loopback, highest loopback address as a router ID. So then I have network 10.1.1.0.0.0.0.255 area 0, and then I have network 2222, say 0.0.0 area 0. Alright, and let me see that what configuration I have done here. Now they try to exchange this neighbor relationship. From there they will go and form the topology table, and finally they will go and form the routing table as well. Okay, so let me quickly see that what command I have given here for the network, because we have used /32, that's why I have given 0.0.0.0.0. Now somewhere you will find that you are moving to loading to full state, and here if we can see that information, in the log message. So we have enabled the debug and OSPF authentication is 0. We haven't put any authentication, so it is telling that OSPF authentication is 0. And here you can see that we have this loading to full message. If you go and check show IP OSPF neighbor, then you can see that you have DR BDR selection already happened. For router 1, he is telling that router 2 is BDR. Now if you go to router 2 and if you check show IP OSPF neighbor, you can see that he will tell who is the DR. So for router 2, this 11111 is the DR, what is the interface, what is the IP address that we have discussed earlier. Now I'll go to switch number 1, and here also I'll go and do this router OSPF say 1, and then I will put the network, for example the loopback address that we have 101.101.101.0.0.0.0 area 0, and then I'll put the network that we want to form the OSPF relationship. So we have a network and with the wildcard bit 0000 to 55. Alright, and within area 0. At the moment I'll do this, I can go and check show IP OSPF neighbor. Now you can see that he is seeing that who is the DR and who is the BDR, correct? The third device. Now if you go here and check the OSPF neighbor, you can see clearly that DR other. So now this IP is DR other. We haven't assigned the router ID manually, but here you can see that they can detect it. Means the router process can go and assign what will be the router IP or router ID for these devices. We can go and check like this, show IP OSPF, and you can see the ID. Now if you want to filter and use that, I try to do with this command, simply you can go and check the ID. That will tell you who is the router ID. Alright, so this is the way that they are going to form the DR and BDR. And if I have one more device in the DR other, then you could find that the process will stuck as two-way state. Okay, so what I'm telling here is that if I am here and if I have one more device connected to this guy here, and that is also working as a DR other, then these two devices, they will form the, they will stuck as a two-way state. They will not exchange the entire topology and database tables, etc. All right, so let's stop here. So let's quickly understand the network type, OSPF metric, and the usefulness of passive interface. Now, OSPF is supporting a wide variety of network type. Here you can see that in OSPF, you have these many network type support. Now, how to memorize this, because you can see it's a big number, this network type. So you can think like this, that you have point to point and you have, see here, so point to point, and then you have point to point, point to multi-point, broadcast and non-broadcast, like you can think. So you have network type broadcast, and then you have network type non-broadcast, and then again if we add with point to point and point to multi-point. So now point to point, obviously we know that point to point is just point to point network, two devices are connecting with each other, it's a point to point network. Then what about point to multi-point? So here you can see that point to multi-point non-broadcast. So you can think that you have point to multi-point broadcast and non-broadcast. Okay, so that means you have 1, then 2 and 3. Apart from that, you have network type broadcast. So you have network type broadcast and you have network type non-broadcast. That means you have total 5 different type of network support. Now again, if you go and check the nature of the broadcast and non-broadcast. So if it is a broadcast, that means the DR/BDR selection will happen and the neighbor will form automatically. Means you don't have to write the manual command to form the neighbor relationship. Correct? But if it is a non-broadcast, and suppose if DR/BDR is forming, you can see that the hello is unicast multicast. When you're seeing unicast means you have to go and use the neighbor command. So you have to manually form the neighbor. Correct? So once we know about the broadcast and non-broadcast, and again you can see the timer as well. For broadcast network is 10 and 40, and for non-broadcast is 30 and 120 seconds. Correct? Now, same concept we can use here. So here you can see that point to multi-point. You can think this is a point to multi-point broadcast. So that's why it's a multicast. Hello. They will not form the DR/BDR because again it's point to point, and you have so many points to point to multi-point. You can think like this. So whenever you have point-to-point network, you are not going to form the DR/BDR because just two devices. Why you will form DR/BDR? Then I get point to multi-point non-broadcast. Now this is non-broadcast, so that's why you have to go and use the neighbor command to form the OSPF neighbor relationship. That's the whole summary we have for the OSPF network type. So let me go back to the theory. Now here you can see that it's a broadcast. So it will do DR/BDR selection, then it is using these multicast addresses. Because this is the broadcast, they will not form the neighborship manually. Automatically they will form point to point. No need to define the neighbors because you have only two ends. They will form the neighbor relationship. Their timers will be 10 and 40 seconds. They are going to use the multicast address. But again, point to multi-point as well. Everything that is valid here for point to point, it will be valid for point to multi-point as well. Okay. Now, then we have non-broadcast. Whenever we are talking about non-broadcast, then you have to go and form the neighbor relationship manually. Now, OSPF will elect DR and BDR, but neighbor relationship will be manual. And that's why we have this summary. This summary, it's easy to memorize. Even no need to recall, but just will make a point that okay, you have point to point, point to multi-point, point to multi-point, non-broadcast, point to multi-point broadcast, and then you have broadcast and non-broadcast network. How we are going to do the configuration? Configuration part is actually very easy. Only one command is there to define the network. You have to go to the interface. Suppose you are over this serial interface, you go to the interface and use this command IP OSPF network. Suppose if you go and type question mark, then you'll get all the options. So is it a broadcast? Is it a non-broadcast? It's a point to point, point to a multi-point, etc. Each and all these options you will get. And if it is using unicast method, means if it is a non-broadcast, then you have to go and define the neighbor. Otherwise, rest of the configurations are standard OSPF configuration. So for example, NBMA, non-broadcast multi-access. So here we are going and defining the network type is a point to multi-point, and if it is a non-broadcast, then you have to go and define the neighbor, right? So just refer this summary and things will become easier. Now OSPF is using cost as a metric. Here you can see the speed and the cost. So for example, for fast Ethernet and above, your cost will be 1, and then you can see for token ring for Ethernet, for token ring 4 Mbps, you can see the cost. Now the lower is better. So if lowest cost is there, that will be the preferred path in the route selection. How we are going to do the basic OSPF configuration, although we have done one lab. So there you have seen that you can go and initiate the OSPF process. You can define the router ID, otherwise it will take the highest loopback or highest physical interface if it is not configured. Then you can define the area, and that's it. So this is the baseline configuration. Now here interesting thing is that we are defining the wildcard bit. And now it is recommended that if you know the exact subnet, so according to that you can use the exact wildcard as well. So suppose if I am using point-to-point network, so I can use, say for example, 172.168.1.0. So here it's 17. So 172.171.0, and then I can use wildcard 0.0.0.3. So like that we can go and use the wildcard wisely. What will happen if we go and initiate the OSPF process, and once we start advertising the network, or once we put this network command, then they will send the hello packet. The neighbor relationship will start working. We know that the steps down, init, two-way, X start, exchange, loading to full. First they will form the neighbor table, then topology table, and finally they will run the SPF algorithm and we'll get the final OSPF routing table. Correct. Now the final thing here in this recording, as was the theory, the passive interface, the concept of passive interface. Now suppose if you don't want to form OSPF relationship, then you can go and make any of these interface as a passive interface. So suppose if I make this interface as a passive, then you can see that the passive means the command prevents update from being sent out or received from this interface. So if I go here in this example, it is showing this interface. So if you go and make this particular interface as a passive, or any interface as a passive, they will not participate in OSPF neighbor relationship. Means they will not send or receive the updates, and that's the usefulness of passive interface. But generally how we are using this command is, uh, we will do this thing, no passive interface E0. Here you can see, first of all, we'll make all the interface as a passive. So the command one is passive interface default. Suppose if you have 10 interface, that means all the 10 interface, you're not sending and receiving the updates. And then you will go and add the interfaces one by one where you want to send or receive the updates. Okay. We have one important note here, that the passive interface command will prevent OSPF and EIGRP from forming neighbor relationship out of that interface. No routing updates are passed in either direction. So this passive interface is true not only for OSPF, but this is true for EIGRP as well. So we are going to stop here, and in next section I will show you a few of the things that we have a study here, like network type, how you can go and change the network type and you can enable the passive interface. Let us do the lab. Here you can see the topology. uh, we have router 1, router 3, and switch 101. I'm using in between switch 105 as a L2 switch, so that means I have area 0. So this big blue circle is area 0, and the network is 10.1.1.0/24. Then I have switch 101 and 102 connected. That is inside area 2020, and the network is 10.1.102.0. So 101 is dot 1 and 102 is dot 2. I have already assigned the IP address. So what we'll do, we'll go and enable the OSPF process. Then we'll go and check the default network type, and then I will make any of the interface as passive interface inside area 0, and then again we'll verify the OSPF neighbor relationship. So let's do this. I can go to router OSPF 1, and even if we are here, we have option that we can run the script as well. So if you are doing the configuration over empty putty, you have this option for a script, say conft router OSPF1, and then you can advertise the network as well. I can select the devices and then I can send the script. Now once OSPF is configured, then I should go and assign the, or I should advertise the network, or should I can use the network command. So what you can do here, you can go and check the IP route, your connected interface, and in the network command, actually, you can go and use it with wildcard bit, and we should check this 10110 is part of area 0. So we know as per our topology this is correct. Then we have one loopback here that will be depend that in which area you want to put. This also I'll put inside area 0. And then I have one more network that is this guy here connected with area 20, area 20. So these are my network command. Likewise, I can go to switch number 2 and I can go and check the connected routes. I can use my network command. First of all, I'll advertise my loopback inside area 20. And then I have my network that is connected, that is inside area 20, because the bottom switch is actually everything is inside area 20. So that's why area 20, area 20. All right. So at the moment we run this command, you'll find that both the switches, they are now interfaces are part of area 20, and they will run the OSPF, and here you can see that the OSPF loading to full means all the states are completed. So I can go and check show IP OSPF neighbor. You can see full BDR and the interface as well. Then we can go and check show IP OSPF, actually show IP route OSPF. So here you can see that you have the metric value and you have the AD value. AD is 110 and the metric is 10 plus 1. So that's why it is 11. We know that for Ethernet interface that is 10, and then 1 is for loopback. So that's why it is showing like this. All right, here you can see the Ethernet. So for that we have 10, and then generally 1 it is using for loopback. All right, next thing that I want to check here is that is show IP OSPF interface, and that is E0/0. Now here you can see that interface where the network type is broadcast. So what I can do that the switch is connected over E00, I can go to the interface E00 and I can make that IP OSPF network as point to point. Now here you can see that you have broadcast, non-broadcast, point to, multi-point, point to point. And if you go to point to multi-point and type question mark, you have point to multi-point. By default, it will be broadcast, and then you have the non-broadcast like that. So I'm interested to make this as point to point, and both side I should do like this. So other side also I should go, and I should go here to E0/0 network point to point. Now you can see that again OSPF process is running. It is going from full to down, and the SPF algorithm is running one more time. And then we have the new tree, SPF tree, and from there we have new routing update or routing table. Show IP OSPF and the interface is E0/0. Here you can see this network is now point to point. You can see this cost as well. There is other information as well related to timers, non-stop forwarding, etc. Alright, so we have done this task with these two switches here. Likewise, I will go and initiate the OSPF process, and I will advertise the network for R1, R2, and only R1 and R2. We don't have any R3. Alright, so let me quickly check here in switch 101 what is the complete OSPF configuration that we have done. So these three network, one network is belonging to the network that we have connected with R1 and R2, that is nothing but the area 0. And then these guys have one loopback address 111 inside area 0. And likewise, I'll go here and then I will use 222 area 0 and then this. Now if I go ahead and check show IP OSPF network, here we have three devices who is forming the OSPF relation. If I go and check show IP OSPF interface, I want to check the interface E0/0. So here I can see that again the network type is broadcast. Now in our topology, either I can use network type as a point to point or broadcast, but we have seen that chart that as per the topology, suppose if you are working or dealing with frame relay, then you can use NBMA and then you have the mode for NBMA, correct? I don't want to make this as a non-broadcast. If you make this non-broadcast, so suppose if I go to R1 and R2, and I should know what is my neighbor, show IP OSPF neighbor, and if I go to interface E0/0 and if I make this IP OSPF network is non-broadcast, then I need to add the neighbor command manually. So now if you check your neighbor, you can say it's a down, because in this case you have to use this neighbor command. So you have to go to router OSPF1 and use the neighbor command. Who is your neighbor? So this guy is your neighbor. Then use the neighbor command. This guy is your neighbor. So manually we are adding the neighbor now, and here also it is detached. So these are my neighbors. I'll go to interface E0/0. IP OSPF network is non-broadcast. Then router OSPF1. We'll go and add the neighbor, this, and again I'll go and add one other neighbor. Then we can go and check show IP OSPF neighbor. Still this is down. Show IP OSPF interface and then E0/0. So now it become non-broadcast, but we are seeing here that the network is down because we are using the wrong network type here. If we have the NBMA type of, or if we have a non-broadcast type of network, then we should go and use here. Again, you can see this hello and dead timer is changing. Okay, so what I'll do here that I'll go and make this interfaces again backup. Interface is 0/0 and IP OSPF network is, say for example, broadcast. So one side is broadcast and other side is non-broadcast at this point of time. And now you can see it is forming the relationship with the switch 101. So if I go and check do show IP OSPF number, you can see it is forming this. Likewise, I'll go here and again interface is 0/0. IP OSPF network is broadcast, and then we can go and check show IP OSPF neighbor. Alright, so now we have to test the final piece, that is the passive interface. So suppose if I go and make one of the interface over R1 as a passive, so let's do that. I can go to router OSPF1. You can see that we have this command passive interface default, and then you can go and make no passive interface. So once you do this command, all the interfaces become passive, means your neighbor is down. So here you have to use no passive interface, and that is the E0/0. E0/0 is the interface. I want to make no passive interface. And again, if I go and check the neighbor, so here you can see this is up. So that was the lab related to whatever we have studied in the previous recording. You can refer this particular lab. Next, we have OSPF authentication and virtual link. So let's start with OSPF authentication. Now, actually, it's very easy to configure and it's different than RIP and EIGRP. What we can do, first of all, we can go to the area. So here you can see I'm over OSPF, I'm inside area, I am putting area 0 authentication. Then I can go to the interface level and then I can go and give the authentication key. So we have two things. We have the plain text or clear text, and then we have MD5. Now same way we can go and configure the MD5 as well. So again you have to go to area 0. Here you can see that I'm over area 0 here and the authentication message digest. Then I will go to the interface and then I can assign the message digest key. So it's very easy and straightforward. I'm going to show you in the lab section about the message digest key, this authentication. So more we can discuss in the lab. Now next thing here is, what about virtual link? Virtual link is again one of the use case we have in OSPF, that for example, due to any reason the customer network, they are not able to directly connect with area 0. We know that all the areas should be connected with area 0. So suppose you have area 1, 2 and 3. For example, later due to some reason you are connecting area 4 with area 3, not with area 0. So in that case, we can create the tunnel in between area 0 and area 4. So the router inside area 4, they will think that I am part of area 0 or I am directly connected with area 0. And that's the concept of virtual link. Again, you will see the configuration here. The configuration, you'll find it's a very much like we are creating that tunnel. So router, the area 1 is working as a transit, and then I have tunnel in between, say for example, area 0 and area other area. So let me go back here. So here you can see this is the classical example that you have area 0, area 1 and area 2, and then you are creating the virtual link in between that. Okay, now there are possibility that you may have area 0 and in between you have area 1, and that's again the possibility is less, but still you can create the virtual link in between that. Now once we create the virtual link, then over the area 0 we have put the message digest. So same key we can put over virtual link as well. Okay, so we have seen all these steps, and let's perform the same task in the lab setup. So we'll understand more about the authentication and the virtual link. Let us perform the lab related to authentication and virtual link. I have done the change in my setup here. You can see that now we have R1, R2, and that's R2, but switch 105, then switch 101, and then switch 102. So R1 switch, and then again switch, and then the switch 102 in the bottom. Subsequent network IP addresses I have changed. So we have network 10.1.1, 10.1.2, 10.1.3.0, and then we have respective area like area 0, area 1, and area 2. Now in lab number 1, we'll go and um, create or run the OSPF in between area 0, and then we'll do the MD5 authentication. In the same lab later on, we have to create the virtual link, and we have to make area 1 as a transit. All right, so let me show you this IP addresses assignment here. You can see that we have created and assigned the IP addresses only so far as per the diagram. So oops, these are the IP addresses assignment related to R1, R2, related to R1 and all the switch. So now let's start with area 0, that is R1 and switch 105. I'll go here and enable router OSPF1. Then I have network, say for example 11111, and then I'll put this inside area 0. So let me do that. Then I have network 10.1.1.0. This also I'll put inside area 0. Alright, now we'll go to the switch, that is switch 105, and we can go and check the network. First of all, we'll go and initiate the OSPF process. Then we have one network, that is 10.1.1.0, but we have 105.105 network as well. So let me quickly do that, and 00000 area 0, for example. Then we have the rest of network. So now you can see I have enabled this, or I ran this command, but still I can't see that OSPF is coming up and running. So I should go and check the IP over E00, and we should have at least IP reachability. So E00 here, it is correct. If I go and check the interface configuration for this switch, so let me try to check 0/0. Wow. So we have this command configured and protocol is up. So if I do the ping, so let me do the ping from here for 10.1.1.1. That's the router IP. And I can see that ping is working. If we could go and check show IP OSPF neighbor, show run section OSPF. So here you can see that I have this network inside area 0, and then I have my network, that's the loopback, but still I can see that they are not forming the neighbor relationship. So now what I'll do, I'll go here and make this network as a 10.1.1.0 area 0, and then I'll remove this network statement. You can see that the problem here we have. Then again I'll go back and delete this and add this. So let me try to do both at a time in router number 1. Okay, and let's try to check. Show IP OSPF neighbor. Now they are in two-way dweller state. They stuck in dweller state. Alright, and if I go here and check in this, because we haven't removed OSPF from here, show IP OSPF neighbor. Okay, so the reason maybe now it is up. Maybe the network type that we haven't changed, but now it is showing it is up and running, so that's okay. Now we have the OSPF relationship over area 0. What I want to do now, that I want to run the authentication. So I can go to router OSPF1 and then area 0 authentication. Here you can see that you can do plain text if you want. You can leave with this authentication, or if you want to do the MD5, that is the more secure, then you can go and use this. Now at the moment I have done this, you can see that the neighbor is up, but we are getting one problem here, that authentication key, you don't have any valid key. So now what I'll do, I'll go to 00 and then IP OSPF authentication. You can see that you have authentication and message digest option. So I can go and put the key as a CCNP. You can see here that you can go to authentication and key, and then you can see here that you have option, say, unencrypted. This is not that I'm looking for, so I can go and give the message digest, but I want to put the key as well. So let's see, IP OSPF authentication, and we can give the authentication if it is a plain text and authentication key. And suppose if I'm using authentication, then I have this option for message and digest. Actually, that is quite a confusing option that Cisco is giving to you. So, because obviously natural thing is that we'll go and check IP/OSPF authentication, and then whatever authentication will be there. But in case of message digest, you should go and check IP/OSPF, and then you have this option of message digest key if you want to put your key. So I'll put key as the CNP, but let's see, yeah, MD5, and then so this is the long command that we need to put here. Now if we go and check show IP OSPF neighbor, we can see that neighbor is down because of mismatch of the, or we don't have the key configured to the other side. So here also we can go to router OSPF1 area 0 and then the authentication message digest, and then we'll go to interface E0/0 IP OSPF message digest key. Now we are getting this error MD5 CCNP. So now you can see that the neighbor is coming back up. So this is the way that we can go and do the authentication inside area 0. Now what I want to do here, that I should go to the I should first of all do the OSPF rest of the configuration, and then we'll create the virtual link. So let me do that. R1 is okay. In R2, let me check show IP route, and what network that we have configured so far. So we have router OSPF1. We should have one more network, that is 10 dot let's see the network. That's 10.1.2.0. So 10.1.2.0 0000255, and that is inside area 1. Correct? So this network is in area 1. Now we have switch number 101. So let's do the configuration for switch number 101. And what network we have? We have network 10.1.3.0, that is in area number 2. Then we have network say 101, 101, 101, 101. So for example, I'll put this in area 1, and then finally I have 10.1.2.0, that is inside area number 1. Alright, so we are very much done with this OSPF configuration. Finally, we have switch number 102, where we have 10.13.0 network. So I'll go here as well and should enable OSPF, and then we have network. Say for example, first of all I'll advertise the loopback, and this is inside area 2. And finally we have network 10.1.3.0, that is again inside area number 2. Now here you will see that after running all these commands, if we go and check show IP OSPF neighbor, so he has neighbor that is 102 and 105. Now if you go here and check to the switch 105, you will find show IP OSPF neighbor. So he should also have two neighbor, but if you go and check show IP route for OSPF, you'll find that he is not getting 102 because it is never getting tunneled or passed through the area 1. So in this case, we should go and create the virtual link. Okay, so let's create the virtual. So I'll go and create the virtual link here inside area number 1. So first of all 105 and then 102. So already we are here, and router OSPF1 area 1, and then the virtual link. What is the ID? So we know that the neighbor ID is this. You can see here that we have option for message digest key as well, that I'll put later on. But that's it. Area, virtual link, and then the peer device router ID. Now I'll go to 101. I'll go here and router OSPF1 area 1 virtual link is what's the router ID you're looking for to make the tunnel. That's sorry, not this one. This is 105. Okay, so I'll go and remove this, and that's it. So once you do this, then if you go here and check the OSPF, you'll find that you will start getting the routes. Now what is happening here in this case, that since you don't have key configured, so inside area 0 we have the key configured. You should go here and give the key so it will work properly. Go here, and here also we'll go and we should give the key, say CCNP, and now you will see that they will start getting the routes. So if if I go here and check show IP OSPF neighbor, now show IP route OSPF, it should get 102.102.102. That will be the final valid verification for this. So after running this command, I can't see that anything is happening. And let me go and check here as well. You can see this configuration is 100% correct. You're creating virtual link with this, and in router 1 also the configuration key, everything is correct, but it's still they are not forming this. So what we can do here, that we can go to router OSPF one more time. Router OSPF 1, area 1, say for example the authentication is message digest. This belongs to area 1, and here also we have area 1 as well. Let's see the final configuration. SPF. Now invalid key for 10/0, that we can verify. So what is happening actually here, that if you go and check the configuration, you'll find that once you are putting the key here over the virtual link, now this belongs to inside area 1. These are the interfaces where you have to put the authentication key. So for example, as a MD5. But when we are creating the virtual link, actually, in that case, that is going to propagate area 0 only. So it's not required to put the key there. Okay. But just for the security purpose, I'll go and put the key over 10/0 and E1/2 as well. So E say 10/0 and IP OSPF, or maybe IP, yeah, OSPF message digest key 1 MD5 CCNP, correct? And then finally I can go here and interface E2/1/2. Wow. So this much configuration we have done. And now if you go and check show IP OSPF neighbor, first of all we should have the neighbor. And if I go to R1 and if I go and check show IP route, so here you can see that it is getting the route as a O routes, as it is directly connected with area 0, and we don't need to put actually authentication over the area 1 interfaces that I have done, but for sake of security we want to put the authentication key at all the places, so you can go and put the authentication keys at all these places. Alright, so this was the authentication. And the next important section, we have OSPF summarization, different type of areas, and the default route concept. So let's start and understand the summarization. Now clearly you can see in the diagram that you have area 0 separated by area 1 and area 2. And for example, if you are getting routes, say 10, 1, 0, 0, 1, 1, 1, 2, 3 up to 7, and other side you can see that is 8, 9 up to 15. Now we are sending all these routes to the core router. Here you can see all the individual route, and hence the database or the topology table of the inside the area 0 will increase. Rather than what we can do, that we can summarize the area 2 as 10.1.8.0 and area 1 as a 10.1.10/21/21. Correct? So in that case, we are sending only one update and our routing table will be efficiently utilized. Doing so, we can reduce the load over the router CPU. So this is one of the interesting use case we have with inter-area OSPF summarization. Now what's the command? Command is very easy and straightforward. We can go to the router, and over the router you can go to the area, and then you have to use the keyword called range, and then you can use the address and the subnet mask, and then this will be done. Now there is one important point to mention, that suppose if you have some of the routes in between that is not part of subnet. So for example, if I don't have 1.5, 1.6, is still I am using this summarization, that is 10.1.0.0/21. So in that case, what we can do, we can use the concept of static route null zero, and we can point out this summary route towards null zero. So that means that anything that is not matching, that will be garbaged. That will be bit bucket. Correct. Now here you can see that note that after 12.16 and now we are running the modern or advanced version of operating system. Even this command is not required. It was required for the earlier version of iOS. Now the second point related to summarization we have is, suppose if the summarization is coming from the external system, it's not related to inter-area routing, but it is coming from outside. Now at this point of time, we should go to the ASBR. Suppose router B is ASBR, who is connected with non-OSPF domain or non-OSPF routing protocol. So in that case, you can do the summarization, but syntax will be little bit different. So in this case, instead of doing area, the command is summary address and then the network and the subnet mask, means whatever network we want to summarize. Correct. So now this concept is very much like we are doing the aggregation, and we have two type of border. We have ABR and we have ASBR, and like that we can easily do the summarization. Now here you can see that we have one use case in case of ASBR summarization, that if you don't want to advertise certain prefixes, so in that case, you can go specifically to that particular network and you can use the keyword called not advertise. If you use not advertise, obviously these networks will not be advertised inside the OSPF. Okay, so this is the concept related to summarization. Now next important concept we have is the OSPF area type. Now I have one summary chart as well where we can go and summarize the OSPF area type after few slides. So here you can see that you have area type called backbone, non-backbone, stub area, totally stubby area, and not so stubby area. That is NSSA in short. So let's learn and discuss about the area type. Now starting with the basic area, that is the normal or the standard area. We know inside that area we have LSA type 1, we have LSA type 2. So here you can see that we have all the LSAs inside the standard area, the type 1, type 2, type 3 and 4 generated by ABR. Then we have type 5 as well, that is generated by the ASBR. So it is able to understand all the LSA. That's the standard area. Now the second thing here, that when you are making a stub, at the moment you will make the area as a stub, the stub will not accept type 3 and type 5. But remember, they will automatically inject the default route. Now doing so, we are not While doing so, you can think like this: while doing so, we are cutting off the SPF calculation. And who is doing the SPF calculation? My CPU, my process. So that means that we are cutting off the intensive cycles, CPU cycles, and hence we are providing good type of optimization in terms of CPU and memory. Correct? Now, what's the command? Again, the CLI command is very easy and straightforward. You can go to the network. So here you can see a router process. First go to the router process, and then you can go to area 1 stub. At the moment you do the stub, that means it will start stopping type 4 and type 5, although it will get router, network, and ABR generated LSA. That is type 1, type 2, and type 3. And other thing is that it is generating the default route. Now the third concept we have is the totally stubby area. Now what totally stubby area event will do, that will accept only type 1 and type 2. It will not accept type 3, type 4, and type 5 LSAs, although it will go and generate the default route for type 3, 4, and 5 LSAs. Again, the use case is that we are saving the bandwidth, we are saving the CPU core, process cycles, etc. Now the command here is interesting, that here we have used in a stub area, we have used area 1 stub. For totally stub area, you have to add one more keyword, that is no summary. So the command is area 1 stub no summary. It will stop LSA 3, 4, 5, and it will generate the default route. Okay. Now the fourth one is not so stubby area. Now, why we need not so stubby area? Here you can see that you may have chance that area 0 is connected with external network, or you may have chance that area 1 is connected with external network. Correct? So in that case, we'll see that when you have area 1 connected with external network and you want to filter some sort of LSA, you are going to use the not so stubby area. Means it's a stubby area, but it's not fully stubby area. What it will do, here we'll see that like a standard stub area, NSSA area routers will share type 1 and type 2 LSAs. Okay, they are not blocking type 1 and type 2. NSSA area will also accept type 3 LSA. So they are going to accept type 1, type 2, type 3. But NSSA will not accept type 4 and type 5. Okay. Now we are going to introduce one new LSA, that is LSA type 7, that we haven't discussed so far, but not so stubby area is linked with LSA type 7. And what's the use of LSA type 7? Now we'll see. So if an ASBR exists within the NSSA area, this is ASBR will generate type 7 LSA. Again, NSSA areas are almost identical to a stub area. If area 1 was configured as NSSA, it would not accept any external route originating from router G as ASBR outside area 1. So here you can see that they are not accepting any type 4 and type 5 LSA. Rather than we have type 7 LSA. So here you can see that it will not accept, this is the router G, it will not accept any external network, external non-OSPF domain network. Correct? Great. However, area 1 also has an ASBR within the area router A. Those external route will be flooded into area 1 as type 7. So here you can see that you have area inside area 1, you have router 1, and who is getting the uh, external routes, and that will be flooded inside area 1. Now these external route will not be forwarded to other area as type 7 LSA. Instead they will convert it into type 5, and that's the key, and that I'm going to summarize. Type 5 LSA by area 1 ABR router C. So what is happening here, when you are creating not so stubby area, in that case you are getting type 7 LSAs, and router C, what he will do, he will convert type 7 LSA to type 5 LSA, and then it will flood it into the other area, or the other area will calculate as per the type 5 LSA update. The configuration is very simple. What you have to do, you have one keyword, go to the route process, and then area 1 NSSA. Okay. All right. And final concept we have is totally not so stub area. So let me stop here, and remaining concept we'll discuss in the next recording. But here you can see the summary, and in this summary, let me try to highlight. Backbone LSA 1, 2, 3, 4, and 5. They are not getting LSA 7. Non-backbone like area 1, area 2, etc. They are also getting all the LSA. Stub area LSA 1, 2, and 3. Totally a stub area, only LSA 1 and 2. Remember, they are going to generate the default routes. The not so stubby area, type 1, type 2, 3, and type 7. This type 7 will be converted to type 5, and then it will be reaching to area 0. That's the overall summary we have with this recording. So let's stop here, and next section will continue from here. Let us continue where we have left off. Now, next concept we have is not totally not so stubby area, that is NSSA. So what is the main difference between a stub and totally a stub area? The same difference you'll find between not so stubby area and totally not so stubby area. Totally not so stubby area will allow LSA type 1 and 2, and he is going to filter type 3, 4, and 5. Here you can see the configuration is very straightforward. You can go to OSPF area, and then you can give area 1 NSSA. The keyword is no summary. And here we have the summary just for your reference. Now the next topic we have is OSPF and relation with default routes. We know that when we are generating to a stub area and totally a stubby area, at that time the OSPF process, they are generating the default route. But in case of ABR and ASBR inside a standard area, we don't have default route. Now suppose you are sending LSA type 3 from router C, and you are expecting that you are getting say LSA type 5 from router 1. So you are getting LSA 5 from router 1, and it will go to router C and then other areas. Likewise, LSA type 3 will go to B and A, and actually B and then A and then the external network. At that time, suppose for the external network, you want to create the gateway as router A, so we can go and create the default route. So here you can see that additionally force router A to generate a default route, including itself as the next hop for the external network, and injects into this inside area 1. Okay, what is the command? Command is router process, go to router process and default information originate. So this will inject the default route. But in case suppose you want to force it, so for example, if a default route does not exist in its routing table, router A can still be forced to advertise a default route using always command. So in that case, if I want to force the default route, lab that what type of IPv6 addressing we are using. So here I'm using this type of lab. You can see we have router R1, R2, R3, 4 and 5. Here you can see 1, 2, 3. These are the router number 4 and 5. Now in this topology, although just for sake of simplicity, I'm using only area 0, but we are not restricted to use just the area 0 piece. We can go and create same type of topology and methodology that we have learned earlier, and multiple areas we can create. All right. Coming back to the addressing, what type of addressing we are using. So we have something loopback either 0 or loopback 1. If it is a router 1, so I'm using 1 and then double colon 1/128 as a loopback IPv6 address. So suppose if it is a router number 4, you can see the numbering, it is router number 4 here, and this is router number 5. Let me clean this and let me write one more time. So suppose if this is router number 4, so IPv6 address over loopback address, either loopback 0 or 1, you'll find 4 colon means double colon, and that will be used inside IPv6 4 and then /128. That's the IPv6 address I'm using for loopback. And what about the interfaces? So suppose if this is router 1 and this is router number 4, so IPv6 address that I'm using here, you'll find 14 colon colon 1/64 here, and then 14 colon colon 2/64 here. Again, if we have router number 2 and router number 3, so I'm using 23 colon 1/64 here, and then 23 colon 2/64 on this interface. So like that, you'll find the address schema, and that's why I haven't put all this information in this diagram. Once you see the lab, you'll understand. Very easy and straightforward, correct? And the configuration and the complete configuration you will find in this particular document as well. So once we go, what we need to do, we have to first of all enable IPv6 routing. You'll see that how we are enabling this and all. So once your OSPF IPv6 means OSPF version 3 is up and running, then you can go and verify the router ID. Now router ID, although you can see that it having number very much, this is showing IPv4 type of numbering. That's right. But the point here is this, that this IPv4 type of numbering that we have related to uh, IPv6, you may think that why not we have something 1:1, something like that here as a router ID. Router IDs are not that much important in IPv6. You can see the notes here. So OSPF v3 picks read router ID, exact algorithm used by OSPF version 2. It is 32-bit dotted notation that we have in OSPF version 2, but has nothing to do with IPv4 address. You can use any format, 0001, 025510, etc. Okay, should not use 0.0.0.0 because it is reserved. Apart from that, you can use any 32-bit dotted notation. Now once we'll go and configure all the routers, and then we'll go and verify router LSA, network LSA, link LSA, inter-area LSA. These are the OSPF version 3 command. I will show you these commands in the lab. Now what's the difference here? So OSPF v3, you can see, is almost similar, and all the LSA types are almost equal to OSPF version 2. We have two new LSA, link LSA and prefix LSA. Now the summary LSA is now called as a inter-area network, and summary ASBR is called as an inter-area router. Correct. Rest of the things you'll find is very much similar. Now, what about the configuration? You can see the configuration. We have 5 routers, so you can see IPv6 related configuration. First of all, we need to go and enable IPv6 unicast routing, and then we can go and do the configuration. So for example, in R1, you can see that loopback 1 having this IP, and then loopback 1. The command is, we can go to the interface. Once we are over the interface, then we can go and run this command, IPv6 OSPF1 area 0, area 2, area 3, etc. But we know that concept that you have one backbone area, and then rest of the areas are connected with that. We have checked all these things in the previous OSPF version 2 section. correct? Then here you can see that how I have given the IPv6 address just for sake of simplicity. So 14::1/64. Then somewhere you'll find 12. So that means if you are at the R1 and if you're going to R4, you'll find 14 address here. And then if you're going to R2, you'll find 12:::, here. Okay, /64. So like that, we have used this strategy, and rest of the configuration are almost same, that we have what we are using inside our OSPF version 2. Although you can see the IP address is related to IPv4 as well, but it's up to us that if we are purely inside the IPv6 network, then these addresses are not required. These are the 4 configuration related to router 1 up to 5. So next, what we want to do here, I will go and show you in the lab section that everything will be up and running. I'll show you that how you can go and check the OSPF neighbor and then few of the LSAs output in the lab. All right, so let's stop here. I will show you the rest of the output in the lab. Now we're ready to perform the lab related to OSPF version 3, and let's do it. So already I have done the configuration, and let me log into all these devices one by one. Let me show you this. So same topology that we have seen earlier in the slide in the PPT. I have all those 5 routers which is running here. They are virtual routers over viral environment, but if you want, you can use GNS3 or any other emulation that is available. Now what we can do here, we can go here and we have this script option, and we can send to all. So let's select all and use show IPv6 interface brief just to see that what IPv6 interfaces we have in configuration. So here you can see that gig is 00, you have your global address, you have the link local addresses as well that is derived there over these interfaces. So gig 01, 02, and likewise you can see all the IPv6 addresses in the same way that we have discussed earlier. If it is R5 to R3, so you will see here 35::5, like that we have the address. Now next, what we want here is that we want to check the OSPF version 3 configuration. So for that, actually we need to go and we can go and check these interfaces. So if you go to these interfaces, only one command is there, that is IPv6 OSPF1 area 0, and apart from that, let me show you that what other configurations we have. So you can see that I have used IPv6 unicast routing. IPv6 was there automatically, and these configurations we have used. Let me highlight these configurations we have used over the interfaces, and now the OSPF is up and running. Now here, if you can go and check the OSPF version 3 neighbor, so you can see here that in broadcast network still it is following the DR BDR rule to form who is the DR BDR, etc. We know that how it is forming. We have done this in the previous sections. And router 2, because router number 2 has 3 connected neighbors. One is router number 1, one is router number 5, one is router number 3. So likewise, you can see here that it is showing you this information, and here you can see the router ID as well. So in this output, you can see the router ID as well, and there are other outputs as well. We can go and check show IPv6 OSPF, and here you can go and check the ID. So here you can see the router ID. We have the router ID. Show IPv6 OSPF also will give you the detailed information, and then if you want, you can go and do the filtering there as well. So I'll go back to router number 2, and here we can go and check different type of LSAs output. So we can go and check show IPv6 OSPF, and once you are there, you can see that what filters you have. You can see good long list of options that we have, but we are looking for database. And after database, you can see that we have options related to router, link, network. You will see the router as well, correct? So if you want to check the router, and then we can go and check the self-originated link status. So here you can see that we have the router LSAs. Likewise, we can go and check the network LSAs as well in IPv6. So instead of router, you can go and use the network and then self-originate. You have the network LSAs. Likewise, we can go and check the link as well, link LSAs. So here you can go and check the link LSAs, and finally you can go and check the prefixes as well. So if we have the prefixes, let's see the prefix self-originate. Great. So this is the way that we can go and check all the LSAs, most of the LSAs, but we know that there is good amount of LSAs. But this is the way that we can go and do the implementation. And then again, after implementation, we can verify as well what's the output we are getting here. And the implementation in all the devices, I told you that I am using only area 0 just to sake of simplicity, but to do the deployment related to version 3, OSPF version 3 is the same. So not a big thing. It's very much same like we are doing inside OSPF version 2. All right, so let's stop here and we'll move to the next section. Now we are ready for the OSPF troubleshooting section. In this section, we are going to discuss some of the troubleshooting use cases, some of the troubleshooting tickets related to OSPF, starting with the path computation. So let me quickly walk you through the topology diagram that we have. We can see that we have big topology diagram, starting with router number 1 to router number 19. And this topology I'm going to use for different use cases, different sections, subsections going to be used. Same topology diagram I have over Cisco viral, and different use cases again we are going to discuss with that. Now in first use case, we are going to discuss about the path in between R1 and R4. So again, before going there, I just wanted to pause here so you can mark it down that what is the IP schema I'm going to use. So suppose if it is R1 and R2 and the address in between, how I have used. So 10 dot, the lowest router number, then the highest router number, and then suppose if you are in router number 1, so last octet will be that router number. So 10 1 2 1, and then /24 will be the IP for router number 1, this interface. Other interface will become 2.2, correct? So 10.1.2.2, like that. Now, if it is a broadcast type of network, such as here you can see. Now, for broadcast type of network, I am going to start with 10.0, and then the router, so lower router, say router number 1, and then the router number, first router, second router, whatever router is there in that list. So for example, R1, R2, R3, so X will become 1, and then X will become 2, and X will become 3. So here the IP is 10.0.1.1. Here the IP will be 10.0.1.2, and in this interface the IP will be 10.0.1.3. Okay, so easy type of address formatting. Two different type of interfaces are there, broadcast and point-to-point, and IP you can understand. Then for loopback, 10.0.0.x, X will be the router. So suppose if it is router 8, so 10.0.0.8. If it is router 19, 10.0.0.19 will be the loopback addresses for the interfaces. So three different type of address schema I have used here. Now let's check use case number 1. So we have some issue in between router number 1 and router number 4. And if you go and trace the path, you'll find to reach from router number 1 to router number 4's loop back. So router number 1 loop back to router number 4 loop back. You have 3 different paths uh, via R14, via R2, via R3, R5. The optimal path, the desired path we have is obviously via R1, R2, and R4. But due to some reason, we may able to send the traffic from R1 to R2 to R4, or the return traffic is coming by this direction or any other direction that we need to figure out. But the problem here is this, that you are facing some sort of latency, slowness in between two peers, and we have to find out that why this issue is. Do you have asymmetric routing, or your traffic is not flowing as per the lowest hop counts, etc. Okay, now obviously we will go and make some hypothesis that, okay, via this path you have some issue, via this path you have issue, via this path you have some congestion, etc. But before starting any troubleshooting ticket, we should have full topology diagram. We should have layer 3 topology diagram, IP schema, the device accessibility, etc. Now, what we can do in this case is, since we are dealing with OSPF, we can go and check the cost value. We know that the metric value is the cost value, and if you see the main topology diagram, you'll find that everything is gig interfaces. So for gig interfaces, the cost value is 1. Although here you can see I have used 1010, but it's okay. You can understand that what you need to do, that for all different paths that we have, so via this path, via this path, via this path, all 3 different paths, we should go and build the cost value or the metric value, correct? And once we go and build this cost value, then we should understand. So we'll come to know that what is the actual path and what is the desired path. The actual path may be via R14 or via R3, R5, but our desired path is from R1 to R2 to R4. You can say R1, R2 to R4, correct? So that we are going to verify once we find out that the issue is there. We can go and resolve it and things will work. So let me go and open the lab. I'm in the lab section, and if you go here to R1, we know that we should check the destination. Destination is 10.0.0.4 with the source 10.0.0.0.1. Let's see the reachability. You can see it's reachable. Like that, I can go to R4, and from R4 also I can go and check the source 10.0.0.4. So you can see that reachability is there, but still there are some issue. So now we can do the trace. We can go and trace the path, the destination with the source, and start this trace. And likewise, I can go to R4 and I can trace, I can go and trace the path. So do the trace route for the destination. From here, the destination is 10.0.0.0.1 and the source is this. All right, so if I go to R1, here you can see that R1 is going to 10.0.1.3. It is going to 1.3 means this is router number 3. This is 3 to 5. Then 3 to 5, then 5 to 4. So you can see it is taking extra path here, how it is going. So when I have started the trace, we check the trace and we'll finding that when we are doing the trace, it is going via this path to reach the destination, from source to destination. And now if you go and check the return traffic, or from 4 to 1, you can see that it is going via R2. This is the desired path. So from one direction we are getting the desired path, other direction we are not getting the desired path. We can go and do the debug. Let's see, debug IP, IP packets, and we can use ACL here, 1310. I'll do 1310. Okay, I'll create that ACL. Oops. You can see so many packets, this multicast packet exchange is happening, and that's the problem we have with the debug. Let me do undebug all and undebug. Let's create the ACL. So access list, and I want to create extended access list 1310. We can give the permit host 10.0.0.0.1 is the source, and the destination. I just wanted to create extended access list. I don't want to create the standard one. So here I can see, let's see in the debug IP packets. And you can see that we can go and use in between 1 to 199, correct? So 101 will be perfectly fine for us, correct? Access list 101, permit the host, okay, permit the IP host 10.0.0.1, and then the host 10.0.0.0.4, okay, enter, and then we can end, and then we can go to the debug IP packets, and then we can give 101. Then if we do the ping or trace route, so let's do the ping. I want to do the ping from the source to the destination, and I want to repeat it 2 times. So let's see. So you're sending, you can see source to destination, I can see source to destination, we can see here, and I want to do one more time this debug detail, and then ping. Great. So now you can see that source to destination, but you're not seeing anything that is coming from 10.0.0.4 to 10.0.0.1, correct? Now, this is one of the way that you can debug with access list, and you can check the result. If you do not use the access list, you have seen earlier that so many packets, so many packet related to hello and others will come into the picture. Great. Now we are going to focus on the classical way, that we want to create the graph theory, OSPF graph path, and then we want to check it. So if I go here and check the route related to OSPF, and we are very much focused on the path that we want to reach here. So you can see that 4, okay, great. And now if you go to R4, show IP route OSPF, you can see here 3. Now the desired troubleshooting is this, that we can go to hop by hop and we should check. So if router 4 has to come here, or it will go here. So you can go and check the comparative cost, correct? Then here to here, you can check the comparative cost. And suppose this is the destination in terms we are coming as a return traffic. So to reach to here, what will be the cost? So cost here, cost here, cost here. And to reach in this direction, what will be the cost? So if the cost in this path will be lesser, obviously that it will go via the longest path, correct? So that we want to correct here, and you can see here R4. Likewise, we can go and check this to R2. We can go and check this to R3 and R5 as well. So what is the intermediate devices? See R5, R3. Okay. So let me quickly go here to R5. At least one hop we can go and check. Okay. So here, let me reconnect my host. And once it will come, we can go and check show IP route related to OSPF. And you can see here to reach, it has one path that is going via 3 because it is assuming lower metric. Okay. So you can see somewhere you will find the highest metric. So if you go via the router 14, you can see via router 14, it has 25, correct? And if you check R4, let's see the 14, 24. So that's why it is not taking the path. So now we have actually two paths only. So this path, because of high cost value, is not desired. So we have two paths. We have to troubleshoot this path and this path. Because while doing the troubleshooting related to trace route, we found that the 1 to 4 traffic is going via this path, but return we have some issue. So that means some cost values related to OSPF, those are coming into the picture. And if it is related to cost value, we should check this guy here and we should check this guy here, the cost value to R2 and R5. Better, we can make the cost value common to all the devices, correct? So if I go here and check to R4, let's start with R4. Show run section OSPF. Do we have any cost configured here? No. Now we can go to the peering devices, correct? So I should go and verify two devices. One is R5, one is R2. So let's go to R5, which is already open. And here you can go and check. Okay, do we have any cost value? No, you don't have. Show run section cost. Oops. If cost is configured, so it will tell you. So if cost is not there, that means that you should go and check R2 first. Show run section cost. Inside R2, I can see so many costs are configured. Let's see how many interfaces we have here. So we have 4 physical interfaces, and if you go and check all the interfaces one by one, so cost 1 place, cost 22, that is going towards router number 14, that I don't want to do any change. Let's see 3, and let's see 4 as well. Cost, so that is going to router number 4. So that means if I go here to interface kick 0/4 and I can do no IP OSPF cost, remove this cost value. Okay, and now once we remove this cost value, then let's see when we have done the trace route. Again, we can go and check the metric values and we can do the trace as well. So let me try the trace. And from R4 as well, I just wanted to do the trace one more time because we have corrected the cost value here. So one change we have done in a network, and after that change, because anyways capturing the trace result as well. Wow. Anyways, let the debug going on. It's no problem with that. Undebug all. Let's do undebug all and let's run the trace one more time. Meanwhile, let's see router number 4. So router number 4 path is good now. And what about router number 1? Let's wait and watch. It's coming up. So it's going to router number 2. Then it's going to router number 4. That's 100% correct. So now you can see router number 4 and router number 1 is behaving properly. Great. So you can see that we have done the OSPF path manipulation, and we are now able to find the optimal path from router number 1 to router number 4 and 4 to 1. In this lab, we are going to see that if we have issue related to OSPF adjacency, that means that OSPF, they are not forming the adjacency. What are the common issues? What are the common problems we have? We have to gather the problems and then we have to fix it. In our lab diagram, we have two routers, router number 2 and router number 10. So in between these two devices, in between these two routers, they are not forming the adjacency, and there may be any issue, means there may be n number of issues that we have to go and fix it. Maybe the link is down, maybe it's passive, maybe authentication misconfiguration, maybe router ID misconfiguration, wrong IP, any type of security configuration, stub configuration, etc. Okay, so what we need to do here, we have to go check the configuration, we have to go do the troubleshooting, and we need to fix the issue. Okay, so I will go log into router number 2, router number 10. I will try to identify the issue and then we'll try to fix it. Okay, what we can do here, you can see that we have a debugging option. We can go and check the debug condition over the interface. We can go and check the debug IP OSPF packets as well. Okay, so let's start this. Let's check the configuration, what configuration we have and how we can solve it. Now, if we go to router number 10, and if we go and check the debug condition, and we need the interface, what interface we have, this particular neighbor. This particular neighbor is forming over gig 0/2. And here you can see that condition 1 is set. Then we can go and check the debug IP OSPF. And then you can see that we have multiple options. The popular ones are adjacency and then packet. So I can go and enable the packet option here. Okay, so we have on the debugging, and at the moment I on the debugging, you can see that we are getting some sort of authentication failure. So clearly it is showing that we have some sort of authentication mismatch. Now, if we go and check this particular interface, let's see that what authentication configuration we have here. I can see plain text in Cisco 123. And if we go here and if we verify inside router number 2, what authentication we have on the router number 2, and let's see, this interface is gigi 0/3. Show run interface gigi 0/3. Here you can see the authentication is a small Cisco 123. So that means either any of the place you have to go and you have to correct the authentication parameter. So I can go to router number 2 and then I can give Cisco with capital C 123, and we have fixed this authentication. So let's see the debug message. It should not come now. It's telling that area 0 had some authentication in and out. It should be corrected now. Still, I can see that authentication is coming, mismatch is coming. Again, we'll verify this interface. So authentication key, Cisco 123. And here, authentication key, Cisco 123. So I can see that authentication is working fine. And again, interface gig 0/3. Let me redo this configuration. So what is the message? Uh, the version 2, type 1 length, read area, checksum, auth1. Okay. All right. So we have fixed that authentication, but still we are getting the authentication related message. So what we will do next, I can see that one extra configuration we have here is called TTL security. I should not have TTL security here. So I will go and negate that. No IP OSPF TTL security. Remove that configuration from here. And let's see. At the moment, I'm still getting the authentication issue. So over this interface, what I will do, let's remove the authentication first of all. Later on, we'll go and put that. At the moment, we just wanted to fix the issue. And once the issue will get fixed, then we'll go and revert back the configuration. So one place I have removed that, other place also I should go and remove that authentication. Oops. And here also I can go and remove the authentication key, that is Cisco 123. Okay, so both the interfaces I have removed that authentication 0/2. Clearly you can see that there is no authentication configured. And oops, here also I could go and verify 0/3 on this interface. So authentication is gone. Let's see if I can ping to the destination. The destination IP is 10 to 1010, 10 to 1010. And still I can see that there are some issues going on, checksum and auth0. Same type of message we are still getting. So what we can do here next, that we should go and verify that the IP subnet should be 100% correct. So one side I can see that IP subnet is 192, and other side you can see this IP subnet is /24. So that means that over gig 0/3 should have the correct IP subnet, and that I will go and correct from one side 255.255.255.0. Okay, and then we can go and do the ping. So let me do the ping from here to 10 to 1010. And let me do the ping here 10 to 10 to. Okay, so you can see that we have corrected the authentication, we have corrected the TTL security, we have corrected the IP subnet, whatever wrong subnet was there. Still, we can see that something related to area, which is not allowing this to form the neighbor relationship. So now we should go and check the OSPF configuration. And 10 to 10.0 is inside area 1. Okay. And from this side also, We can go and check the router OSPF configuration, and 10 to 10 is in area 1. But I can see some stub is configured. So router OSPF1, no area 1 is stub. I don't want the stub configuration. And we have removed that stub. Now I can see these messages, they are coming fastly. But although these messages are coming, maybe this is belonging to some other subnet or something, but show IP OSPF neighbor. Do I have 10.10.02 neighbor configured? Some checksum, some bad auth, and debug. Let me remove this debugging. Undebug all. And here also we can go and check show IP OSPF neighbor. I can see that I have my peer 32 seconds dead timer. Now what we can do here, we can go and check show IP route OSPF. And we know that the network that we have associated to this particular subnet, and if you go and see behind the network, what subnets are there. So R2, R10. So R2 should get the network related to 10.9 or this router ID 10.0.0.0.9. So let's go here to the R2 and you should see 10.0.0.9. So first of all, let's check here in the R10. So IP route OSPF 10.0.0.0.9 is there, and he should advertise this route to its neighbor as well. So 10.0.0.9 is missing, but apart from that, do we have any other network to verify? Quickly, we'll go and verify other as well. So do we have 11? Do we have this network? Let's see. So inside R2, do we have 10? I can't see other network. So you can see that we have 10, we don't have 9, we don't have 11. So that means that neighbor is there, but they are not advertising their adjacencies. But anyways, that's okay because you can see that this is area 1 and again this is area 0. So other way around, that means I have to go inside R9 and check that these routes are coming to R9 or not. But this particular issue got resolved because we just wanted to form the neighbor relationship in between R2 and R10. And yes, we are able to form the neighbor relationship in between R2 and R10. There are different type of issues, maybe configuration, maybe a stub configured, maybe authentication, maybe OSPF security configuration, etc. But one by one, we have corrected all those problems. And now we have the adjacency form in between router 2 and in between router.
Thanks everyone for enrolling this course. In this course, you will learn all the technologies related to Ccie Ei Enterprise. But in case you are looking and you are preparing for your lab exam, please feel free to contact. We are running some sort of 100% guarantee program to make you pass. I will provide you the lab, resources, everything. If you want to know more about this offer, you can go and email to this particular address. Anyways, In this course, you are going to learn all the technologies. This will be very useful course to you. But in case you are planning to write your lab exam, just feel free to contact us. We'll provide you all the guidance, all lab related tips, techniques, all the passing techniques, etc. So please do not hesitate. Feel free to contact us and we will provide you and we will assure you that you pass your lab exam in first attempt. Thank you. Hello everyone. I'm going to give you offer related to CCI lab. In this lab, what you will find, so let me quickly show you that. In this lab, you have multiples switches. You can see you have more than 16 switches, 20 routers. You have SD-WAN full-fledged lab. Actually, this is complete CCI Enterprise 1.0 lab, where you can do section 1, section 2, section 3. Maybe you know that in CCI exam, you have 3 different sections. Means already sections are defined, but generally these 3 sections that students are practicing. And in this 3 sections, you can perform everything, all the tasks you can perform in this particular EVE-NG lab. You can see the version and the supported images. This is exact match that we have in the exam as well. So for example, for SD-WAN, you need to work on vEdges and the vManage. Release is 18.4. That's the same release we have in the exam as well. So this will be your very much similar lab setup that you have in your CCI exam for your practice purpose. Now, what you can't do in this lab, you can't do lab related to DNA because in this EVE-NG lab, we don't have Cisco DNAC integration, and you can't do ICE lab as well because in this we don't have ICE integration as well. For that practice, you need full-fledged online rake from any good place. You can go and have it. But apart from that, apart from 2.1, 2.2, actually, you can go and perform all the tasks. Even if you are not practicing for your CCI exam, for example, you are practicing for your CCNP and you want to check your OSPF knowledge, BGP knowledge, MPLS knowledge, SD-WAN knowledge, all those tasks you can go and perform in this lab. With this lab, I'm providing the video guide how to do all those tasks. Even we have the lab guide as well. So you can simply follow those guide. You can simply go and complete all those tasks. Suppose if you are new to the technology, so I have multiple free videos in YouTube and Udemy that you can go and refer to upskill your knowledge to learn the technology. And then simply you can go and use this particular lab and you can break any CCNP, CCI exam. Means you will pass it easily. Now, what is the cost? And these are the sections that we have in the CCI exam. So what is the cost of this? Because I'm offering this for the students, so I put very little a small cost here. So you have to pay only 150 USD to get this particular software. And how you can go and get it, you have to email me. So my email address, you can send me one email request. Let me write here, Ratnesh721 Kumar 721 @gmail.com. Just email me and send me the request and I will give you this particular nice software, full-fledged software, EVE-NG software or the file where you can go and practice your CCNA, CCNP, CCI, SD-WAN, full-fledged SD-WAN is there. So if you can go and watch my YouTube videos, in YouTube I have 22 hours SD-WAN video recording file and so many SD-WAN videos I have uploaded in YouTube. Those YouTube videos also you need some lab setup, right, to practice. So even if you're not preparing for your CCNP or CCI, simply you want to learn Cisco SD-WAN, you can go watch my free videos in YouTube, use this particular lab setup and you can perform your SD-WAN. You can become master in the SD-WAN. Likewise, if you're preparing for CCNP, and CCNP, again, we know that we have N core and one elective. For that also, you can go and perform all the tasks related to routing and switching, OSPF, BGP, everything in this lab. It's a full-fledged lab. So I will recommend you to send this email right away. Take this particular lab, practice, enhance your skill, and become very good in the market so you will get high paid salaries. All right. After that, you go and watch the technology video. Thanks for watching.